Jorgensen's bonding description was incorrect for coordination compounds. Alfred Werner had a different idea. He described bonding in coordination compounds between ligands, counterions, and metal atoms or ions. What do I mean by that? Well, there were two different types of bonds that could form between the cobalt and the ligands, or counterions. The lines that are solid, that are directly drawn between the chlorides and the cobalt, represent the primary valence. These bonds satisfy the charge or oxidation state on the metal cation. So CO has a charge of +3 in this compound. 3 Cl minuses must bond to the CO to balance the charge. These are more like ionic bonds. When you put this compound in water, 3 Cl's should dissociate from it. The secondary valence is commonly called the coordination number. This is the number of ligands that are bonded to the central atom, also known as the inner sphere. In this diagram, they are represented by the dashed lines. So all of the NH3 groups are bonded to the cobalt by dashed lines. Ligands that bond to the metal cation through to satisfy the secondary valence do not dissociate from the cobalt when placed in water. So Werner proposed structures as well for the compounds that Werner proposed structures as well for the cobalt-containing compounds. In the first structure, the 3 chlorides satisfy the primary valence, whereas the 6 NH3s satisfy the secondary valence. When this compound is put in water, the 3 chlorides should dissociate from the cobalt, meaning this should form a highly conducting solution and precipitate 3 moles of AgCl per 1 mole of this compound. This is consistent with the experimental observations. In this second compound, 2 chlorides satisfy the primary valence. 1, 2, 3, 4, 5 ammonias satisfy the secondary valence. 1 chloride has a solid line and a dashed line to it. That means this chloride satisfies both the primary valence and secondary valence. Since it satisfies the secondary valence, it cannot dissociate from this compound. Therefore, this should have a medium conductivity and should form 2 moles of AgCl per mole of this compound. Finally, over here we have 1 chloride satisfying the primary valence of this compound, 4 ammonias satisfying the secondary valence, and 2 chlorides satisfying both the primary and secondary valence. Therefore, this compound should have low conductivity and should form 1 mole of AgCl per mole of the compound. All of this data is consistent with what scientists observed experimentally. Now, let's get back to the troublesome one, the iridium compound. Using Werner structures, all 3 chlorides satisfy both the primary valence and secondary valence in this compound. And the NH3s satisfy only the secondary valence. That means all three chlorides should be directly bonded to the iridium and should not dissociate when placed in water. There should be zero conductivity from this compound, and that is what is observed. Werner's ideas of primary and secondary valence explain the properties of these compounds.